In this topic, we move from high-level concepts into the actual machinery behind eIDAS. You'll see how PKI, identity protocols, and key service components fit together, like Lego bricks, to power compliant digital identities and qualified electronic signatures. You've already seen the what and why of digital identity and eIDAS. Now we shift to the how by unpacking the technical plumbing that makes those ideas real. Then we'll plug these pieces into a concrete banking journey and architecture. eIDAS defines the outcomes we must achieve: legally trusted identities, cross-border recognition, and qualified signatures. It deliberately stops short of prescribing every technical detail, though. That's where the building blocks come in. PKI, identity protocols, and service components translate legal requirements into working systems you can design, evaluate, and later reuse in concrete solutions. PKI is built on pairs of keys that always belong together. Your private key is like a highly protected stamp. Only you control it, and it's used to create digital signatures or decrypt data sent to you. Your public key is the matching part you hand out freely. Others can use it to encrypt data for you, or to verify that a signature was really created with your private key, ensuring integrity and authenticity. Digital certificates are like passports for public keys. They bundle a public key together with identity information, then have that bundle signed by a trusted certificate authority. Because most systems trust the CA's own certificate, they can trust what it has signed. By chaining from an end-user certificate up through intermediate CAs to a root CA and checking against eIDAS trust lists, we get EU-wide verifiable trust in digital identities. In our banking scenario, PKI does two big jobs. First, authentication. A user or system proves, "I am who I claim," by showing they control a private key linked to a certificate. Think of this as a very strong cryptographic login. Second, digital signing. The private key signs a document hash, creating a signature that proves who signed and that nothing changed, in a way eIDAS can treat as legally binding. Identity protocols act as the rules of the road for digital identity. A user authenticates once with an identity provider, and the protocol lets another system trust that login without ever seeing the password. Instead, it receives a signed token containing only the attributes it needs. In eIDAS environments, these shared rules let banks, national eIDs, and remote signature services all interoperate securely, instead of building custom connections for every pair of systems. SAML really shines in enterprise and government single sign-on, especially where strong legal identities matter. Think HR portals, government services, or cross-border eIDAS scenarios. Compared with OAuth and OpenID Connect, SAML's payload is an XML assertion that explicitly states a specific person is authenticated and lists verified attributes. The IDP is trusted to vouch for identity, and the service provider relies on that signed assertion to decide access. OAuth 2.0 and OpenID Connect are the glue behind many sign-in with your bank-style flows. OAuth issues access tokens so one system, like a banking app, can call another system's API on behalf of the user. OpenID Connect adds who the user is via ID tokens. Together, they let banks delegate login and signing to trusted identity or signature providers, while still enforcing precise permissions and keeping credentials in one secure place. Across SAML, OAuth, and OpenID Connect, the core pattern is the same. A trusted server issues a token or assertion containing claims about the user or their permissions and signs it so no one can tamper with it. Browser flows then use HTTP redirects to shuttle the user between the application and the identity provider. In our bank scenario, those redirects eventually deliver a token back to the bank, which it uses to continue the process, such as starting a signing session. In an eIDAS solution, four main building blocks work together. First, the eIDAS node or gateway connects national eID schemes with other countries, translating between different systems. Next, the identity provider authenticates the user and sends standardized attributes to whoever needs them. Then, a signature or trust service turns those identities into legally robust electronic signatures and certificates. Finally, banking or business backends consume these results for onboarding and secure transactions. Here, eIDAS acts as the translation layer between a foreign citizen's eID and your bank. the national identity provider actually authenticates the user, using their trusted method like a smart card or banking app. Its assertion is sent to the eIDAS node, which normalizes it into a common EU-wide format. Your bank consumes these standardized attributes to run KYC checks and safely open the account, without ever handling foreign login mechanics itself. This is where the verified identity becomes a legally binding signature. The remote signature service guards the private key inside secure hardware and exposes APIs to create advanced or qualified signatures. The customer never sees that complexity. They simply use a web or mobile signing interface, review the document, see clear trust signals, give consent, and confirm. Behind that click, the service signs the document and returns both the signed file and auditable evidence. Now let's connect the dots behind the scenes. The onboarding or KYC engine pulls identity attributes from IDPs or eIDAS nodes, applies business rules, and decides whether the customer can proceed. Once approved, the core banking system opens the account and stores the golden customer record. In parallel, the document management system generates and versions the contract. Integration flows then route data to signature services and evidence stores, so every step is logged and defensible for eIDAS compliance. You've now seen how PKI gives you the trust foundation, identity protocols move tokens securely, and eIDAS components combine into complete onboarding and signing flows. With this blueprint in mind, we'll next ground everything in a concrete banking use case and design an end-to-end compliant architecture.